that's there. Okay, yeah, so Kevin, thanks for being here, and I'll hand it over to you.
Let me do a screen share. Does the screen share look okay?
Yep, I can see it.
I see. I see some sort of weird green artifact in the screen share. Is that something everyone can see or just me?
Yeah, I can see it as well.
Oh, great.
I'm not...
Just Zoom doing its thing. Let me try and share the whole screen, which I think can be done. Yeah. Does this work better?
Yeah, that's better.
Okay. All right. Okay. Thanks. So I'll be talking about program induction, which is an approach to AI. And the idea is that you build systems which represent their knowledge as programs, as symbolic code. And what that means is that if these systems are going to be learning, then they're going to be adding to that body of knowledge, meaning making new programs or doing program synthesis. So to give some, I'm going to give some examples of why you might want to do this and different kinds of systems in this space, and then place what I'm doing within that environment. So there's a few different ways of motivating program induction. One is that programs tend to be, they tend to generalize very strongly outside of the test cases or data on which they're based. And because they generalize more strongly than like other statistical learning approaches, you typically learn them from much less data. Programs also tend to be pretty interpretable. Not all programs are interpretable, a point which I'll return to later in this talk. But in general, programs tend to be more human understandable than other kinds of representations. So to see this, contrast a programmatic representation of a physical object, like a mechanical drill, shown here as a CAD program, and the analogous point cloud or mesh representation. The program representation is much easier to understand and remix and take apart in different ways. But really, the most famous feature of programs is their Turing completeness, or their universal expressivity. And this means that, at least in principle, they can be used to encode solutions to the full range of problems that we might want to solve in AI systems. So there's a number of program induction systems that have been developed. I think maybe one of the most famous ones is this in Flashfill, which learns programs that edit text. But there's also more recent and kind of more exotic program induction systems like CAD program synthesis systems, which can take as input a shape and then output a procedural representation of how to construct that shape. So core to both of these systems and other systems in this genre is a kind of domain-specific language, a programming language which is tuned for editing text in the case of Flashfill, or for procedurally constructing shapes in the case of this Zelinsky CAD synthesis system. And if you look at other programming systems like this work by Brendan Lake, which is kind of a system for learning and perception of visual concepts, the story is still the same. There's some kind of domain-specific language and some kind of domain-specific synthesis strategy that operates over that language. So I think that the challenge that that poses to us as AI researchers, going back to this picture, is to say, how could we learn something like this domain-specific language so that instead of having to bake in a particular language for a particular class of problems, we could have a system which kind of grows its language in order to tune itself to a class of problems. So I'm going to be talking about a system which does exactly that. And I'm going to think of this as like a kind of learning to learn. Like if program induction is a kind of learning, then we're learning to program induction, so we're learning to learn. So concretely, in order to operationalize this, there's, I think, two main things you need to acquire in order to learn to induce programs. One is you need a library of abstractions. You need the right kind of programming language for expressing solutions to a domain of problems. But even if I give you that language, that doesn't mean you can actually use it to solve problems. You also need a synthesis algorithm or an inference strategy, which can look at a particular task, a particular synthesis problem, and say, this is the kind of code you need to write in your language in order to solve it. So to make this more concrete and like a small toy example, imagine that you're trying to write programs which fit points on some curve. So your system would take as input a curve, and then some learned program inducer would spit out something which had like cubic functions in it. So in order to make a system which could do this, it would need to know first about cubic functions. It would need to have that abstraction in its library or in its language. And also the system needs to be able to eyeball this curve. And just by looking at it and saying that it goes like this, know that this is going to be a cubic function. So it should use its cubic function abstraction. So we have a system which jointly learns these things, which jointly learns these abstractions, and also this inference strategy. And I want to illustrate the abstraction learning first through a concrete program synthesis example. So imagine that you have a program synthesizer and you want to get it to sort a list of numbers. So you might give some input-output examples like those shown on the right, where an input list is sorted and transformed to the output list. And initially, you might give it some set of primitives, which in theory can be used to express a sorting algorithm, but which are not really very well customized to sorting. So maybe you have things like map and fold and conditionals. So somehow we gotta span the gap from the stuff on the left to the stuff on the right. So what the system does is it doesn't just learn how to sort numbers, it takes as input a corpus of interrelated program induction problems, and it tries to solve them all jointly. And in the process of solving these problems, it builds up new abstractions in its library. So it writes new code in its library, which builds upon the code that it has so far. So if you look at its learned library of abstractions, one of the first things that it builds is this thing that the system called concept4, because it was the fourth function that it decided to add to its library. And if you look at the source code for it, it uses the fold primitive, which was built into it. And if I were to give a name to it as a human being, I would call it filter, because it is this high order function that takes a predicate and a list and filters out all the elements that do not satisfy that predicate. So filter would be useful for sorting a list of numbers, but it's still pretty far away from sorting. And if you look deeper into this library of abstractions, what you see is that the 13th function that it learned, which builds on top of filter, takes the maximum element of a list. And that's much closer to sorting. And if you look into one of the later concepts that it learns, you find a function which effectively computes the nth largest element of a list. And this looks like we're almost all the way to a sorting algorithm. And so once it has this function, it's able to write some code which sorts a list of numbers. And it's fairly, I think, human understandable. What this code does is it repeatedly invokes concept 15, and it just says, get the nth largest number, where n is 1, 2, 3, 4, etc. So in principle, you could sort a list of numbers without this learned library of abstractions. You could just use the initial primitives. And here's what the sorting algorithm looks like rewritten in terms of the initial primitives. This program here is, on the surface, it doesn't obviously have anything to do with sorting. It's sort of an obfuscated sorting algorithm. It's not just uninterpretable, but in a practical sense, it's also inaccessible. There's no like reasonably bounded search that could ever find this solution in the initial primitives. In particular, the learned solution, which uses the library of abstractions, the system found after about 10 minutes of search. But if you were to do a kind of brute force search in the initial primitives without any learning, it would take far longer in the age of the universe to discover this sorting algorithm. So now I want to explain the algorithm that built up this library and which learned this sorting algorithm. So this algorithm is called Dreamcoder, and the reason why it has this name is because it's an example of what in the machine learning community is called a wake-sleep algorithm. So other examples of wake-sleep algorithms are things that are used for unsupervised training of neural networks, like the Helmholtz machine. So in the context of Dreamcoder, the wake phase of the wake-sleep algorithm is means performing program synthesis. So looking at your corpus of problems, trying to synthesize programs that solve them. And then it alternates a pair of interleaved sleep phases, one of which I'm calling abstraction sleep because it builds the library of abstractions. And one of which, for reasons that I'll clarify later, I'm calling dream sleep. And what dream sleep does is it trains a neural network to perform inference or to help guide the program synthesis process. So from a kind of Bayesian point of view, the picture you should have in your head is that we observe a bunch of program synthesis tasks. which I've shown at the bottom, and each of those is solved by a program shown in the middle. And at the top, there's some kind of library, like that network of functions I was showing you earlier. And we want you to inference both of the program that solves each of these synthesis tasks, as well as the library, which will give us a language for writing down programs that solve many different tasks. So just to foreshadow the outlines of the approach, one way that you can imagine doing inference in this model is just to guess an initial library and then use that to do inference of the programs, and then pop back up and solve for a new library, and just kind of alternate this process in an EM-like fashion until you converged on both a library and a collection of programs. So I bolded this Dector et al. Citation because the idea for this came from that paper. So one twist we're going to add here is we're going to have a neural network, which I'm going to call a recognition model, whose job it is to look at a particular task and predict a distribution over programs that are likely to solve it. So we're both training the neural network in tandem with learning the library and doing synthesis that gives us the programs. So if you look at this picture here, there's really three different things that we don't know. We don't know the library, we don't know the programs, and we don't know the neural network. And that motivates a three-step iterative learning procedure. And those correspond to the wake phase as well as the two sleep phases. So during the waking phase, what we do is we solve synthesis problems. So we take some synthesis task and we take our library, and our recognition model, the neural network, biases a search over the space of expressions written using that library, and we search until we either solve that task or we reach a timeout. During the dreaming phase of sleep, we train our neural network, the recognition model, and this neural network is going to be trained on pairs of programs and tasks. But where should those program task pairs come from? So one answer is to use the programs that we just found during waking. So we can take experiences from waking where we found some program solving some task, and we can just replay those experiences and tell the neural network, when you see this task, solve it using this program. But a much more interesting source of training data is to construct what are called fantasies in the wake-sleep literature, to sample from your library to build random programs, run them to see what they do, and then teach the neural network based on this infinite stream of random programs. The advantage of this fantasy data is that we can draw as many samples as we want, so we can train on an effectively unlimited amount of data. During the abstraction phase of sleep, we train, or we grow out this library of abstractions. And the way that works is through a kind of automated refactoring. So we take programs that we found during waking, and we refactor them to try and find common subtrees that we can compress out and add to our library of abstractions. So
Yisong had a question. What signal does a timeout give to the sleep phase?
We don't get a signal from timeouts. If we time out, then we just ignore that data point. So I want to zoom in on this abstraction phase of sleep and explain how it works, because it uses some ideas from the programming languages community that I think might be more generally useful. So this is the learning of DSL part of the system. And I want to start with a very simple program and then explain some ways that it could be refactored and how that could give rise to new abstractions in the library. So the example program is just 5 plus 5, which in Python I would write like this. And in Lisp, I would write it like this. And as a syntax tree, I would write it like this. So I want to look at the syntax tree and think of different ways of refactoring it. So one way that I could refactor it is to define a new function, which I'm going to call 5 plus x, or lambda plus 5x, and set x equal to 5. Another way I could refactor is define a function called which computes x plus 5 and set x equal to 5. Or I could define a function which computes x plus x with x equal to 5. Or I could also create a function which just computes 5 plus 5 and set x equal to 5, even though x does not occur free in 5 plus 5. And all of these different syntax trees are different ways of rewriting the original expression, which I'm going to notate with this dashed orange arrow. So this dashed orange arrow just means that these things are semantically equivalent. So now if you look at all of these different refactorings, they all look basically the same. The only difference is whether these leaves are an X or a 5. And you can collapse together all of these refactorings into one data structure like this if you introduce this new operator, which I'm calling any, which means a kind of non-deterministic choice. It means you can choose any of my children, and no matter which child you choose, you will still respect the semantic equivalences indicated by the orange dashed lines. So we build out this data structure, which has these any operators and which tracks these equivalences. And the data structure contains other kinds of refactorings. So for example, we could, instead of abstracting out the number 5, we could abstract out the plus sign. Or we could even dive into the syntax tree and refactor the number 5. And the reason why we're building this data structure is because it's representing an exponentially large set of possible refactorings. So in particular, for each of these any nodes, we have 2 choices. And if you percolate those random choices up through the syntax tree, what you get is this kind of repeated doubling action, which leads to an exponential growth in the number of refactorings that we're encoding in this data structure. So now I want to explain how building this data structure can be used to refactor code in ways which gives you new abstractions for your library. So here are 2 programs that are very similar. One computes 5 plus 5, and one computes 4 plus 4. Here's a subset of the data structure in each case. And I want to zoom in on 2 parts of this data structure, one that I've called A and one that I've called B. And A and B look very similar. They just differ in whether one of the leaves is a 4 or a 5. And both A and B are effectively encoding a set of possible programs. And you can intersect those sets just by recursively walking the corresponding trees in the data structure. And if you look at the intersection of these 2 sets, you get this expression here, which is just lambda x plus x. And you could write it in Lisp like this. And if I were to give a name to it, I would call it double, because what it does is it takes a number and it doubles it. And you can imagine that if you had a whole bunch of expressions like 5 plus 5 and 4 plus 4 and 3 plus 3, then it would kind of pay off to add this doubling abstraction to your library. And the sense of paying off, the sense of compressing the syntax trees is the objective that drives the library learning. So I now want to give an example of this library learning procedure for something that's less trivial than learning how to double numbers. So imagine that you have to solve a bunch of programming problems, and you start out with just the Y Combinator, so like primitive recursion, and a few other basic operators like cons and char and conditionals. And you have 2 different tasks to solve. On the right, the task is to, given a list of numbers, double each number in that list. And as shown on the left, the task is to take a list of numbers and increment each element. So now, if your programming language doesn't have the operator map, the higher order function that takes a list and a procedure and applies a procedure to each element, then it's still possible to solve these tasks, but it's very effortful. You have to write a lot of code in order to do it. And I've shown here the code that the system discovers when solving each of these tasks. So during the abstraction phase of sleep, the system takes these programs that are found during waking and it refactors them, so it builds out that data structure. And in each of these cases, it constructs about 10 to the 14th different possible refactorings. And I've shown in each of these boxes one member of that set of 10 to the 14 refactorings and highlighted in orange a subtree that those refactorings have in common. Now, if you pull out that orange bit that they have in common and add it to your library, then all of a sudden it's much easier to write down these programs. So the orange piece that was pulled out corresponds to the higher order function map. And once you have map in your library, writing down these programs is much easier. You can just say map a function which doubles and map a function which decrements. So this is much more interpretable, and it's also much more, it's much easier for search to find these short programs than it is to find these long programs. 10 to the 14 is kind of a scary number. In practice, it doesn't actually have to explicitly construct 10 to the 14 different things in memory. The data structure for encoding these refactorings takes about 10 to the 6 nodes, and it takes about 5 minutes to do this particular refactoring. So that was how we learn a library. So we're compressing things down into our library, and I'm going to explain how the algorithm jointly learns a neural network for guiding the synthesis process.
Okay. Sorry to interrupt. A quick question. So Eric asked, how does the system manage the trade-off between the library size and the complexity?
Yeah. So that's a good question. We have a prior which favors library components which minimize the total size of the library and the size of the programs when encoded using that library. So we're trying to jointly compress the library and the programs. So going to this picture, I'm going to talk now about the dreaming phase of sleep, where we're training this neural network to predict a distribution over programs that are likely to solve a particular task. So conceptually, you can think of this as some neural network that takes as input a task, like some input-output examples, and outputs a program. But really, a better way of thinking about it is a neural network which takes as input a task and outputs a distribution over programs from which you can draw samples to propose programs that might solve that particular task. So there's different things that this neural network could be. So for example, it could be a recurrent neural network, like in the robust fill system. So think of it as like an image captioning model where you take as input a task and sort of caption it with the program that would solve that task. The neural network could be a unigram model, so it could predict a distribution over, or it could predict probabilities for each of the primitives in the library and trade off between which primitives are more likely to be used. What we found is a nice kind of sweet spot is a bigram model over program syntax trees. So bigram models, ordinarily you think of them as being distributions over strings, and here we're thinking of them as distributions over trees. So the way that that works concretely is as follows. The probability distribution is really a conditional, the neural network is predicting a conditional distribution over the child node in a syntax tree, given what the parent node is and given which child it is. So if your syntax tree starts with a plus, then the neural network predicts a distribution over what the left child of the plus sign should be. And here it predicts something which put a lot of probability mass on the number 9. And it also predicts a distribution over what the right child should be. And here it predicts something which put a lot of probability mass on multiplication. And then you can recursively unroll this and draw samples from this bigram model. So there's a couple reasons why we chose this bigram model. One is that the neural network only has to run once per task, because it just has to run once in order to output this bigram transition matrix. So that means that we're bottlenecked by our CPU cycles, not how many GPUs we have, because we don't have to repeatedly go back to the GPU to ask it what the transition probabilities are. The second reason why we do this is because it allows us to learn to break syntactic symmetries. So for example, we can learn that conditioned on the parent being a multiplication operation, we shouldn't have any of the children be the number 1, because then we would just be multiplying by 1, and that's not very useful. So now I want to go into some experimental results, and I'm going to focus on what kind of synergy there is between learning a DSL, between learning this library of abstractions, and learning the synthesis procedure, so learning the neural network that biases search. So we've applied this to some variety of different domains. A lot of them sort of look like programming problems, but some of them look more like drawing pictures or solving simple kinds of planning problems. I'm going to focus on programs for drawing pictures, for planning to build things, and for doing recursive programming and discovering equations. So for drawing pictures, what we did is we built a corpus of geometric drawing problems like these. So the problem is to look at an image and then write a program which will draw that image. And we initially equipped the system with a library of turtle graphics routines. So it has control over a pen that it moves over a canvas, and it has some control flow operators, and its goal is to write a program which matches the same pixels as in the input image. So when you run the system on this collection of drawings, the output is as follows. So on the left, what I'm showing are the initial primitives given to the system. On the right are a few example drawings. Underneath each of them is the program it wrote for that drawing. And in the middle are the abstractions in its learned library. And arrows in between abstractions indicate which abstractions call which other ones earlier. So to dig into this more, if you look at this kind of swirly beach ball picture, you can see that the way that it drew this is by calling out to learned function 8, fn8, and learned function 4, fn4. So fn4 draws spirals. It draws a parametric family of different kinds of spiral-like things. And that makes sense because when you look at this swirly beach ball thing, it kind of looks like a bunch of spirals repeated. If you look at function 8, what it does is it takes a drawing routine and then repeats it around in a circle-like pattern. So function 8 is really the concept of radial symmetry. It takes as input it's a higher order function that takes as input a body, some drawing routine, and then repeats that body around in a circle some number of times. And if you look into this library, you see other things like routines for drawing circles and polygons and things like that. And the reason why it's learning these is because they're broadly useful for drawing many different kinds of figures. So
sorry, there are two questions. So I guess first one question was in terms of the neural network that you use to predict the distribution, what is the representation of the input? Is it like a CNN or does it have the symbolic?
It's a CNN that looks at the pixels.
Okay. And there was a second question. Have you considered generating programs for 3D scenes, for example, for Blender?
We have considered that, and me and lots of other people have been thinking about that and doing stuff in that space. We haven't applied this system to that problem. So this library of functions is kind of like the system's declarative knowledge, like it's explicit symbolic representation of the domain, but while it's learning this is also training that neural network. And the neural network is trained on fantasies or dreams. And it's useful to look at how those dreams change over the course of the system's learning trajectory. So at the initial point of learning, before it's built out this library, this is what random dreams tend to look like. So I've color-coded these to show how the system drew each of these images. It started drawing where the color is pink, and then it ended up drawing where it's kind of a dark purple. And you can see that some of these have nice structure, but for the most part, these don't look like very interesting drawings. This is mostly not the kind of stuff you want to train your neural network on. And in fact, these examples are kind of cherry-picked. If you draw random samples from the system before any learning, they mostly just look like empty canvases or straight lines. So this is not the kind of data you would want to train your neural network on. So now after learning, after it's built out that library, which has things like spiral drawing routines and polygon drawing routines, we should expect to see much more interesting dreams. So after learning, dreams look more like this. And for fair comparison, these are also cherry-picked from the same number of samples as I showed you earlier. So these look more complex than the training data, and that's because these are the most interesting ones selected from a pool, just like we did earlier. And if you look at these samples, what you see is a kind of remixing or recomposition of the kind of latent concepts or motifs that are in the training data. So it'll learn things like radial symmetries and polygon drawing routines, and then compose them in new ways and generate this endless stream of synthetic training data. So by learning the library, the neural network gets better training data. So we also tested it on a very similar domain where instead of giving it control over a pen and having it move over a canvas, we gave it control over a kind of hand in like a Tetris world. And it was tasked with building towers out of simulated blocks. So each task is to build a target tower. And if you look at its learned library, you see abstractions which kind of look like macros or options. Like they're higher level abstractions which allow it to plan in bigger steps. So it learns things like how to build pyramids and bridges and things like that. And you can look at the dreams before learning, and you can look at the dreams after learning. And again, what you see is that by learning the library, the trained data becomes much richer and much more varied, and it looks much more like the actual tasks that it has to solve. So it's also useful to look at the system's learning trajectory over time. So here on the x-axis, I'm plotting how many wake-sleep cycles it's gone through. And on the y-axis, I'm plotting how many test problems it can solve within a 10-minute timeout. So at the initial state of learning, most of these tower building problems are not solvable. But after a few cycles, it's able to solve some of the easy problems and then bootstrap off of those solutions. And then after a few iterations, converges to solving most of the problems. You might be thinking, like, do we really need both of these sleep phases? Because even a single sleep phase should have that property of bootstrapping off of its own solutions. And what we find is that if you ablate either of these sleep phases, you get much lower asymptotic performance. There's a few kind of baselines we can pair with as a sanity check. I think the most important baseline is this enumeration baseline. And this enumeration baseline, shown in a solid dark line, is just what happens if you don't do any learning at all and just do a huge amount of search on each problem individually. So in particular, the black line is the result of doing exhaustive search for 24 hours on each problem individually. And what you see is that without learning, you kind of just don't get off the ground. In purple, I'm showing the exploration compression algorithm, which was one of the main inspirations for Dreamcoder. And in the dashed line, I'm showing a neural program synthesis approach, RobustFill, which just trains a actually very sophisticated neural network on random data.
So Yisong has a question. What happens if you just sleep a lot and then wake up once at the end? Is that something you tried?
So you wouldn't be able to learn the library because the library is trained on actual solutions to actual problems. You would be able to train the neural network though on dreams. We haven't tried that exactly. I think that it would be hard to really get off the ground without looking at least some actual problems. But if you started out with a DSL that was already pretty good, then just sleeping a lot at the beginning, I think, might do pretty well.
And one more question. How sensitive is the learning to the training data? It seems like some of the tasks are very incremental.
Yeah, so that it varies across domains. So for the tower building, as I'll show on the next slide, it does really the best on the tower building domain, because tower building is like the domain that I designed. So it's kind of like a basic sanity check. For some of the other domains, where you'll see like a more slow learning curve, like I'll point to one on the next slide, like that's using data that was crawled from the web and things like that. So it is sensitive to like how curriculum-y the training data is. Here in error bars, what I'm showing you is the variation across different random permutations of the training data. So it's relatively insensitive to the order in which it's exposed to these problems. But as you'll see next, it is sensitive to the actual existence of like what problems you actually have. Like you do need some kind of curriculum. So here, if you look across many different domains, you see the same basic kind of picture, but you see that like the learning curve varies a lot. So like these are like text editing problems from Cygus, and it's not doing as well. But you still see basically the same kind of qualitative picture that learning unfolds over the course of between like 5 and 15 wake sleep cycles, and that both of these sleep phases, learning the library and learning the neural recognition model, are important for bootstrapping the system. So I think that there's a kind of synergy between these sleep phases, and I want to explain qualitatively how that synergy works. So there's a reason why both of these sleep phases tend to push up the performance. So the synergy works as follows. During waking, we solve problems. And as we solve problems, we have more data from which to train our library. But as our library gets better, as you saw earlier, the dreams become a richer source of training data for the neural network. And so that improves our neural net. But as our neural net improves, that causes us to solve more problems during waking. And this creates a kind of positive feedback cycle where when one part of the system improves, it tends to improve the other parts of the system as well. So there's also some data from the experiments which supports this view. And that data comes from looking at the evolution of the library structure over the system's training trajectory. So here, what I'm plotting on the x-axis is a statistic of the library structure, which is just its average depth when viewed as a network. And on the y-axis, I'm plotting how many testing problems are solved. In darker shade, I'm showing wake-sleep cycles earlier on in training. And in lighter shade, I'm showing later on in training. So what you can see is that over the course of training, the libraries become deeper, and that deeper libraries are correlated with solving more testing problems. And if you ablate the neural recognition model, if you get rid of that dream phase of sleep, then you see two things. One is that the libraries become shallower. So your libraries change when you don't have this extra sleep phase. And also for a given library structure, performance is lower. So there's really two things going on. Dreaming gives you better libraries, and also it gives you better performance for a fixed library. And if instead of looking at the average library depth, you look at the total library size, you get the same kind of qualitative picture, although the relationship is a little bit weaker. Now I'm going to go through two kind of stress tests or sanity checks on the library learning. So previously in these experiments, we gave it an initial language which very much like a generic programming language. So for example, the logographics language had like logographics routines, whereas the text editing language just didn't have that kind of stuff. So in theory, we should be able to go further and start with something which looks more like a generic programming language and learn something that looks more like an actual DSL. So I'm going to look at two case studies here, one that learns a language for physics and vector algebra, starting with something that looks like a functional language like Haskell, and one which starts with a very old kind of Lisp and then learns something like that functional language. So for physics, what we did is we took equations from the AP Physics and MCAT cheat sheet, and then we converted them into symbolic regression problems by simulating random input outputs from each of these equations. And then we asked the system to come up with programs which fit that random data. The twist here, though, is that instead of giving it vector algebra routines, we gave it list manipulation routines and expressed all the vectors as lists of numbers. So on the right, I'm showing a few example physics equations, and on the left, I'm showing you the initial primitives that were given to the system. So it's things like map and fold, but also some stuff like the number pi and exponentiation. So if you look at the first layer of learned abstractions, what you see is that it's first building out routines for vector algebra. So it learns about things like adding and subtracting vectors or scaling vectors. And then as you go deeper into this library of abstractions, what you see are things like routines for integrating second derivatives over time. And if you go into the final layer, what you see are things like schemas for inverse square laws. And once you have all of these routines, you can then, in a very compact way, write programs which fit the data from most of these physics equations. And I think that for the most part, these programs are fairly interpretable. So for example, the programs for Coulomb's law just says, apply the inverse square law schema to the displacement vector, which you get by subtracting the positions of the two particles. And if you were to rewrite this in terms of the initial primitives, it wouldn't be obvious at all that this had anything to do with Coulomb's law. So by learning this library, things became more tractable and also more human understandable. So here we built in things like map and fold, but routines like that can also be learned from a more minimal basis. So what we did is we made a kind of problem set of around 20 different functional programming exercises, a few of which are shown on the right. And on the left, we gave it a very basic set of functional programming primitives like cons and car and quitter. And crucially here, it has the Y Combinator. So it can actually do arbitrary recursion. So in the first layer of its learned abstractions, what it does is it defines these two routines called fold and unfold. So fold, as you probably know, is a routine that recursively consumes a list. And unfold is a little more rare. It's a routine which recursively produces a list. And in a sense, these two operations are kind of like two different basis vectors that together can span the set of routines that operate over recursive data. So once you have fold and unfold, you actually don't need the Y Combinator anymore in order to express recursive operations over lists. And what we find is that once it has fold and unfold, it then proceeds to never use the Y Combinator. So it defines routines like map and filter in the fold family, and like range from the Python programming language. That's an example of an unfold. And then there's other routines like indexing lists, which bring together the fold and unfold families. This style of programming, where instead of using explicit recursion, you use folding and unfolding, is sometimes called origami programming. And I really like this exposition of it in this book by Jeremy Givens. And once you have this folding and unfolding basis, it's much easier to express recursive routines. One catch here, though, is that because it was starting from a very Spartan but generic basis, like you just had like the Y Combinator, this took a very large amount of compute. So in particular, this took about a year of compute time. And in practice, we ran it for about 5 days on 64 CPUs. So there's sort of two reasons why I'm telling you this particular story. One is that I think it illustrates a broader point, which is that you're not really stuck with the symbols you start with. Like here, I started out with the Y Combinator, but then after 1 or 2 wake sleep cycles, it did a kind of change of basis and switched into this origami programming basis. The other reason why I'm telling you this story is because I see this as a kind of sanity check on the library learning routine. And I want to make clear that I'm not saying that you should build systems that start with just the Y Combinator or with combinatorial logic or with Turing machines or something like that. Like one of the cool things about programs is that we know a lot about how to make good program representations. And so we can build in things like map and fold. And so we don't actually have to do this experiment that I'm showing you right now. So some lessons from this talk that you should take away from this, I think, are that, I started out saying that programs are very interpretable, and in some sense they are, but they really are not, like, not all programs are interpretable. But by learning this library and by having a bias toward compressive abstractions, it's possible to grow out a programming language which is both better for search and also, I think, generally more human understandable. The second thing, which I think was illustrated in the origami programming bit, is that maybe you could learn from scratch and just start with some generic Turing complete basis, but you don't have to do it. Like, we know a lot about what kinds of things we can build in, but the kind of machinery introduced here, you should really see it as like a way of building in what you know how to build in and then learning on top of that. So now I want to just pose a few different questions and point to some work that I think is making progress on answering those questions.
Just before we move on, Yi-Sung had a question whether you've considered applying this kind of idea to unsupervised program learning, where the wake phase is just hallucinated tasks. So in some sense, sleeping for the whole time. Is that something you've thought about?
I'm sorry, the dog growled during the question.
Sure. The question is, can you imagine a form of unsupervised program learning where the wake phase is just hallucinated tasks? So in some sense, just sleeping the whole time. Is that something you think would be?
Yeah. That is something that we've been thinking about. I think that the challenge there is in coming up with a way of generating good tasks, something better than just randomly sampling source code. So I don't have any slides on it here, but one thing that we've been looking at is ways of defining objective functions which kind of bias it toward interesting problems. And one thing that seemed to kind of work, or at least seemed promising, was to try and find programs which are short, but where the neural recognition model is not able to guess the program solution, or the condition on the program's output, the recognition model cannot guess what the program is. So intuitively, these are problems which are essentially easy because they're short or medium-sized programs, but it's not easy to solve them at a glance. The neural network cannot look at the problem and then immediately output exactly how to solve it. So I guess the answer to the question is, I think we should do that. I wanted to conclude by proposing a few next steps and pointing to some other work in this space. So all of the work here is in some sense neural symbolic, because we are training neural networks to aid symbolic learning systems. But at the end of the day, everything that the system outputs, all the solutions, all the programs, they're all symbolic code. But not everything in the world is crisp and symbolic. How do we learn neurosymbolic programs? But how do we also learn domain-specific languages or libraries for neurosymbolic programs? And there's this work by Luke Hewitt I wanted to give a shout out to, because it's was sort of concurrent work with Dreamcoder, and it also finds that like a kind of wake sleep framing lets you build an algorithm which does something like that. Search is still hard. Even with this neural recognition model, the programs that we're synthesizing at the end of the day are fairly small, but a lot of the code we want to write we might want systems which can construct large bodies of code, especially we want to have systems which automatically discover models or things like that. And some work in this space that me and my collaborators have done is this REPL paper, which incrementally builds out large programs. And I think that we might be able to combine ideas like that with Dreamcoder to help us scale to larger programs and not need like a year of compute time in order to do some of these things. But really, I think that main unresolved question is the fact that we're not really learning DSLs here at all. We're learning a library, and a DSL is a much richer object. It also has data structures and types and like an entire grammar over the space of ways that you can compose the primitives in the language, which might be more restrictive than what is licensed by the type system. And if we want to actually learn DSLs, if we want to actually have a system which can like recover a lot of the DSL-based synthesis that's already been done, then we need to take this last challenge very seriously. So that's it. And I wanted to thank all of you for coming to the talk, and also thank the really cool collaborators I got to work with on this. So that's it. I'll take questions.
Okay. Yeah, thanks for the great talk. So I guess there are a couple questions I'll finish reading, and then I might just unmute people so they can ask their own questions. I guess the first one is from Clement. Do you think what do you think is the relation, or what do you think is the role that Dreamcoder might play in artificial general intelligence?
It's hard to answer that question. So I want to zoom in on the middle word there, general. Like in some sense, programs have the promise of generality. They are a class of universal function approximators, and they do enjoy some nice sample complexity properties. At the same time, not everything that we want to represent is well modeled as symbolic code. So I think that if you want to really make a general purpose learning machine, then it's not going to be code all the way down. You're also going to need knowledge representations which look more like statistical models. So it would really be like if you were to play a role in increasingly general learning algorithms, then the role I would see it playing would be either as part of the program learning module of the more general learner, or as a kind of general architecture for iteratively solving problems and then improving the expertise in problem solving through this wake-sleep cyclic framework.
Got it. So next question from Yisong was, what's the relative time spent in different phases? Does one phase dominate the compute time?
Yeah, so the wake phase is the shortest phase of the algorithm. So it spends around 10 minutes actually doing synthesis. I mean, this is spread over like between 30 and 100 CPUs. So all of these numbers should be multiplied by 30 to 100. And then for training the neural network, it spends about an hour per iteration. And then for learning the library, it spends on the order of maybe 1 to 2 hours per iteration. So it's really, it spends most of its time sleeping.
Okay, and I guess one more question was, I think how much did the error bars in Dreamcoder cost? I think in terms of computation, like how long did it take to?
Like how many?
I'm not sure exactly what that question is asking.
Like what was the compute budget required in order to make the graphs?
Yeah.
Yeah, a lot. Because we ran it over different random seeds and with different ablations and baselines. So it was a lot of CPU hours. Like maybe on the order of maybe 500 run. But then we had to do like 5 runs for the error bars and then different, it took a lot of compute, which is one spot where we need to improve this algorithm.
Okay, so I think now I will go ahead and unmute or allow people to unmute themselves if they have additional questions, or they can continue typing it in the chat box. Are there any other, does anyone else have any questions they would like to ask?
I just have a comment about Dreamcoder. So I used it, I think it was just 2 days ago. I downloaded the, like I set it up on my system, and the really cool thing about Dreamcoder, like the technical implementation of it, is that when you run your experiment, you get a pickle object that where you can inspect the entire execution trace, which I think is a really powerful tool. So thank you, Kevin.
No problem. We're trying to make it usable. Yeah, no, I mean, the code is on my GitHub. I'll put like a link to it on my webpage if you want to play with it.
Yeah, I'm sorry to be dominating the Q&A, but if no one else has a question, I have another question. That's okay.
Oh, yeah.
Okay. So you mentioned that you wanted to have maximal compression in the sense of like having a compact library and having compact programs. And I want to maybe just more broadly speaking question that premise. Like NumPy has a gigantic library and it's okay.
Yeah,
so,
yeah.
So maybe it's more of a philosophical question rather than specific to the project that you did, which is great. It just, you know, in general, it seems like I would not want to be constrained to this premise of having a compact library.
Right, yeah. No, I agree. I think that the reason, so I agree that that is probably, so clearly that's not the objective humans have when they write libraries. If you have a synthesis algorithm which is basically doing some kind of enumeration, which is what we're doing. I mean, it's biased by a neural network, but it's essentially doing enumeration. Then the search complexity is going to be something like 2 to the number of bits needed in order to write down the program. And so if you want to make your search times be low, then you want to optimally compress. And that's the main reason why in this system, optimal compression is the only objective function for library learning.
Okay, so to some extent, it boils down to an interplay, if you will, between how intelligent you can make the search algorithm.
Yeah. So like one of the reasons why NumPy has kind of an over-complete basis is, I think, because people have lots of different ways of thinking about matrix manipulations. We have lots of words for pointing to different kinds of matrix operations. And we want NumPy to kind of conform to the way that our language and our education has told us to think about linear algebra. So that way you can just think about what you want to do in linear algebra and then translate it into NumPy. The system doesn't have any of that. It doesn't know about linear algebra or anything like that. So it just wants like a efficient way of spanning the space of computations.
Okay, one more question on the chat from Eric Liu was, what is the reason for a small library to enable search during synthesis?
Yeah. Like imagine a version of a human written library where you just took every function and you duplicated it and reversed the name of the function. As a human, I wouldn't have a whole lot more trouble using that library. It'd be annoying, but it wouldn't be too bad. Whereas if you're a program synthesizer, you've just doubled your branching factor, which is going to torpedo the search. Unless your neural network is really good at singling out which primitives you need to use in order to solve a specific problem, this is going to completely gum up the search procedure. So you want to find, like, you want to add new things to your library, but only when on net you get compression.
I have a question about the use of version spaces in for GitHub. I'm wondering, like, is it in principle possible to have all of the code of GitHub in a version space, and it being like accessible in a similar way that Dreamcoder accesses its version spaces?
In principle, I think you could do something like that. I mean, one idea that I've heard floated by people who work on equivalence graphs is that you just kind of have one big equivalence graph that has all the code ever and all queries anyone's ever made. And you just do all your queries in this one big graph. And this should amortize the cost of like lots of queries.
Right. And so why aren't people like doing this?
I think that the main reason is because when people write equivalence graph code or version space code, it's always for like a kind of a weird programming language, like a DSL that's used by a synthesizer, or lambda calculus in the case of Dreamcoder. And so you can't really, I can't crawl GitHub for lambda calculus. I would have to like write some egraph code for Python or something. And then, you know, crawl all the Python files. I think that there's also some like unresolved technical issues with egraphs and things like that. Like, you know, the fact that you can't compactly encode equivalences that have to do with the closure of both associativity and commutativity, like that tends to blow things up. And, you know, like there's nothing in this system which, or the system that I've described, Dreamcoder, which gets around those problems. So there's also could be some like things with the algorithm which make it so that it would be hard to do that.
I see.
But
do you think
you might want to do?
Do you get a partial credit doing research? Let's say you build a tower that's kind of like just a little bit off from your actual tower. Like, do you consider that a good build, or is it, do you like reward that program and put it in as a success, or do you not do that in your solving problem phase?
So for most of the domains, we get like a 0-1 reward signal. But for some of them, we do get some kind of partial credit. So for example, in one of the domains, the one I said was based on data crawled from the web, we're trying to learn regular expressions for matching text we found on the web. And you get partial credit depending on how well the regex singles out the text you're trying to match. Or when we're doing symbolic regression, there's a smooth penalty which rewards solutions which use fewer continuous parameters. From a kind of Bayesian point of view, there's nothing problematic about that. You can just fold all of that uncertainty into the graphical model that I was diagramming earlier, where programs generate tasks. Like you can sort of soak up all the uncertainty in that part of the graphical model. But I think that there's some details in how we do the library learning that might not play nicely with solutions that are totally wrong but get some partial credit, because then you might end up adding stuff to your library which is like an abstraction you built from crappy solutions. And you kind of need to know when a solution is so bad that even though it's getting partial credit, you shouldn't try to pull out new abstractions from it and reuse it because it's just a garbage solution.
Okay. And one last question from me. The curriculum you give it to the system are fairly few, right? So you give it maybe like 10 or 20 towers or something like that, and then you want it to learn a library to draw those 20 or 30, right? It's no more than 1,000 example that you give it, right? So like, I guess you already see where the rest of the sentence will be, right? I will ask that, you know, maybe these examples are given kind of in an informative fashion that the user is trying to teach the system like different parts of the library that it needs to learn, right? Maybe it builds a really tall tower or like a very wide small tower, and they are like, can you interpret these intents in some way that, you know, these examples are not random, right, in a way?
Yeah, like could you make something which is a learner that knows is trying to be taught?
Yeah, or like how would you annotate? I guess you could, can you like give a pair of tower and have the user have some kind of annotation, say, oh yeah, they should use something different between these two towers. That would be great. Like something of that.
So I think that natural language might give you those kinds of cues. Like if you had some natural language alongside each of the tasks.
Okay.
You know, Kathy, who's one of the main collaborators on this project, took the lead on some like follow-up work which explores this. Each task has some natural language, and you use the natural language to tell the system what kinds of tasks are related, and it biases what kinds of things it adds to its library. So I think that, you know, if you want to make a system which knows it's being taught and which can learn from far fewer examples. So like usually we're training the system on between like 50 and 100 examples. But you can imagine that, you know, if you had some language that told you what examples are related and how they're related, just because they share keywords or something, then maybe you would only need like a dozen examples.
Thank you very much.
Yeah, I have a question. Have you considered using a Dreamcoder as an educational tool, or do you think it could be potentially used as an educational tool?
I think it could be used to maybe teach people OCaml and propose ways of refactoring their code. Something like that.
That's awesome.
Like you can imagine putting the refactoring into like an IDE where you highlight two little pieces of code and say like, what's a function that would let me more compactly express these two pieces of code?
Oh no, so as an educational tool, like literally like kids learn to program Dreamcoder, to implement modules for Dreamcoder. So they have a program synthesis, like an interpreter and a neural network. It's like a fully scoped class.
Oh, I see. So instead of writing code, they write input-output examples.
No. They implement the modules for Dreamcoder to implement a new domain.
Ah, I see. I think the code base right now is not up to that challenge of being good pedagogy for people learning to code.
But do you think it can be good pedagogy for maybe like a group of 5 students that are committed, that want to like get their hands dirty in the code base?
Yeah, I'm trying to think of what unique aspect of Dreamcoder would make it better positioned for that than like another software project or another program synthesizer. And I guess the main thing that I can think of is that, you know, if you use it to teach like a group of 5 people or something how to code, then they would learn both about some PL stuff and also some deep learning stuff. So it, you know, like if you had like a class on like neurosymbolic synthesis or something, then, you know, you could call out to routines from that for like solving homework problems from that class or something.
That's awesome. Yeah, great. Thanks.
Okay. Are there any last questions? I think we should wrap up soon, but I think if anyone has that. Okay. In that case, thanks, Kevin, for the great talk, and hope to see all of you here next time.
All right. Thank you, Osbert.
Bye.
Thanks, Kevin. Bye-bye.